Good morning. Today I'll be going through electrochemistry part 2, focusing on electrolysis for the A-level chemistry. Hopefully it will not be too long. Please remember to support me by clicking subscribe to receive the most updated information regarding A-level chemistry and O-level chemistry information. Now, so this will be the content for today's lesson. We'll be covering the factors that affect how much substance could be liberated during electrolysis, looking at some industrial uses of electrolysis and the relationship between Faraday constant and Avogadro constant to solve problems. Now, last lesson, we discussed the applications of electrochemical or voltage cell, where it is a spontaneous redox reaction that provides the source of electrical power, where chemical energy was converted back to electrical energy. In today's lesson, the focus is on electrolytic cell, which supply electrical energy to make non-spontaneous redox reaction, where electrical energy is converted to chemical energy. So the process of passing electricity from external source to force a non-spontaneous redox reaction is called electrolysis. And the cell where electrolysis occurs is the electrolytic cell. So these are the components in a typical electrolytic cell. We have the external source, which is the battery, and we have electron flow from this electrode, which is called the anode. So the chemical species will lose electron here, and oxidation occurs at the anode, where electrons are transferred from the anode towards the cathode. The cathode receive the electrons or accept the electrons and have reduction occurring there. The electrolyte is in molten or aqueous state. Cannot be in solid state because it will not be able to conduct electricity. Mostly ionic compounds are used as electrolyte. During electrolysis, there are two possibilities for chemical change. So the electrolyte, the components are oxidized or reduced. The electrode, if we are using a reactive anode, it will be oxidized. So due to the redox processes occurring, some possible physical observations include the change in color of intensity of the electrolyte, bubbling or effervescence observed at the cathode or anode, which indicates the evolution of a gas, or if there's any solid metal deposits on the cathode, or the anode decreases in size where it dissolves in the electrolyte. So just remember, oxidation always occurs at the anode, and cathode is where reduction takes place, red cap. So when we describe substances, we describe them as being either liberated in the terms of, let's say, gases are formed, then discharge means they form solid, something like that. Now, let's compare between the two types of cells. For electrochemical cell, we have spontaneous redox reactions. And for electrolytic cell, it's a non-spontaneous reaction. Non-spontaneous doesn't mean it will not occur. It just needs external assistance. And this comes from the electricity of the external source that force the reaction to occur. And these are the energy conversion. For electrolytic cell, the external source is required, but it's not required for voltage cell. We will need a salt bridge in the voltage cell, but not so for electrolytic cell. The electron flow in the external circuit is still from the anode towards the cathode. But the sign of the electrode will be different between the voltage cell and the electrolytic cell. So for the electrochemical cell, the anode will be assigned the negative sign because that's where electrons are generated and move away from it. As for the cathode, it will be a positive sign to attract the electrons which are negatively charged towards it. But it's different for the electrolytic cell. The oxidation occurs at anode. It is actually a positive sign because the positive sign is corresponding to the positive sign of the battery. So that's where electrons are flowing towards. Okay, so it follows the battery. Cathode will be negative. That's where electrons are flowing towards to. It's coming out from the battery from the negative terminal. What are the factors affecting selective discharge of ions? When an electrical potential is applied across the two electrodes in the electrolytic cell, not all species present undergo simultaneous discharge. In fact, the cation or anion that is discharged is the one that requires the least energy. This is called selective discharge. So the order in which ions are discharged are influenced by the physical state of the electrolyte, the position of ions in the redox series, the relative concentration of the species, and the nature of the electrodes. Now let's compare the electrolysis of molten sodium chloride and dilute sodium chloride. For molten sodium chloride, the ions present are only sodium and chloride ions. We are using the inner electrode, in this case graphite. So at the cathode, the sodium ions migrate to the cathode and is discharged by gaining electrons to be reduced. At the anode, the chloride ions migrate to the anode and is discharged, where the chloride loses electrons and is oxidized. When we combine these two equations together and eliminate the electrons, we will have this as the overall equation. So it's just a decomposition reaction of the ionic compounds. So this is the setup of the diagram, the anode and the cathode. Okay, so we are using molten sodium chloride here as the electrolyte. And at the end of the electrolytic processes, we have chlorine gas forming. And since the temperature remains high, sodium will exist in liquid state or molten state. Because it's denser, it will fall to the bottom. If we look at aqueous sodium chloride, we need to consider presence of water. Okay, so at the cathode, we can have either the reduction of sodium ion or reduction of water, where hydrogen gas is evolved. And hydroxide ion is formed. At the anode, we can have either the oxidation of chloride or the oxidation of water, where oxygen forms as well as hydrogen ion. If more than one species are discharged at the electrode, we need to compare the electrode potentials of the competing species. Okay, so looking at the same example, let's recall from what we've learned last lesson, a more positive enol implies a higher tendency for reduction to occur. And conversely, a less positive enol implies a higher tendency for oxidation to occur. So if you look at these two half equations, okay, we notice that the enol for water is less negative. So comparing to sodium ion, water has a greater tendency to be reduced than sodium ion and is preferentially discharged. So at the cathode, what happened is that the water reduced to form hydrogen and hydroxide ions. And this is a single reaction that takes place at the cathode. The difference is too large for sodium ion to be discharged. So sodium ion lost. At the anode, let's compare their standard electrode potential. Since the enol of oxygen is less positive, water has a greater tendency to be oxidized than chloride. So oxygen is preferentially discharged. So you need to flip this over to see that we are talking about oxidation. So this is less positive, so more likely. Remember, a more positive E0 indicates higher tendency for reduction. A less positive E0 represents higher tendency for oxidation. And remember to flip the equation. And if you combine the two equations, it's basically the decomposition of water. And the remaining electrolyte will just become more concentrated due to less water remaining. So in summary, cations are reduced at the cathode. If more than one cation is present and the concentration of the cations are almost the same, the cation with a more positive E0 value will generally be reduced. Anions are oxidized at the anode. But if we have more than one anion present and the concentration is almost the same, the anion with a less positive E0 value will be oxidized. So if we have aqueous solution, normally we will consider water being reduced and oxidized. Now, the E0 value is used to predict the species to be discharged. It's very under standard condition. However, if the concentration is not standard, not 1 mole per dm cube, we need to consider the effect on the position of equilibrium and hence the value of E under non-standard condition. For example, if we have very high concentration of a particular ion, it may discharge even though the E0 value predict it to be less favorable. Consider the electrolysis of brine concentrated sodium chloride, where you have very high concentration of sodium and chloride ions. Now, at the cathode, even though sodium ion is of a higher concentration, it is not able to override the position of the ions in the redox series because the reduction potential is too negative. So water will still be reduced, not sodium ion. At the anode, because the E0 value is not of a big difference, okay? So when you have increased Cl minus concentration, the position of equilibrium for this equation will shift to the left, such that E0 become much less than plus 1.36. So it becomes less positive than even the oxidation of oxygen. Sorry, oxidation of water. So Cl minus is preferentially discharged to form Cl2 based on this because of the shifting of equilibrium. And when that happens, the E0 value changes to become less positive. The nature of the electrode will affect the reactions occurring in the electrolytic process. However, for inert electrode like graphite or platinum, they do not participate. Therefore, they are considered inert. A reactive electrode is one that participates in the reactions. So the reactive electrode, the anode in particular, must be considered in addition to the species present in the electrolyte. So if we look at copper-2 sulfate solution using copper electrodes, which are reactive, we need to consider the copper electrode being reactive and put them together with the species that may undergo oxidation and see which one has a less positive E0. Okay, so looking at the cathode first, we have copper-2 plus competing with water. And because copper-2 plus have a higher E0 value or more positive E0 value rather, the CO2 plus has a greater tendency to be reduced. So CO2 plus is preferentially discharged. So the reaction at cathode will be the reduction of copper-2 plus. At the anode, you have sulfate, water, and copper from an electrode competing to see which one get oxidized, which one is more likely to happen. So in terms of greater probability, looking at the E0 value, you have to look at the one that is less positive, right? So it will be copper. Copper has the least positive E0 value if you look at it from the other way. So it's preferentially discharged. So this is the setup of the electrolytic process. If inner electrode were used, no change with cathode, but at the anode, it will still be the oxidation of water. Now, this is a summary of the example. You can just take a look yourself. The additional things that are not included earlier will be the observations and some remarks. So for molten sodium chloride using graphite electrode, we will expect to observe a shiny metallic liquid deposit right below the cathode, as well as a greenish yellow gas, which is chlorine discharging at the anode or liberated at the anode. So in general, when we electrolyze molten ionic compound, the metal will be discharged as a liquid or solid at the cathode, and the non-metal discharged at the anode as diatomic gases if we are using halogens. And for aqueous sodium chloride, it will be different. Then in this case, we will have oxygen and hydrogen gas liberated at the respective electrode. The volume ratio between H2 and O2 will be 2:1 because mole ratio equal volume ratio of gases based on Avogadro law of gas. Often, the electrolysis of a dilute aqueous solution is in fact the electrolysis of water. But we need to consider that the H plus and OH minus concentration from the auto ionization of water is far too low. Though yes, they are there, but it is not significant enough to be considered in this case. And take note that if the chloride concentration is high enough, there will be a shift of the position of equilibrium to the left to make the E0 value less positive and increase the chance, which means Cl minus will be discharged instead of water getting oxidized. In the case where we have a reactive electrode using copper, for example, observation include copper cathode increases in size and copper anode decreases in size. So try not to say mass because when they say observation, they never ask you to measure the mass. So just say in terms of the size as what you have observed directly without doing any measurement of mass. In terms of the color, no change because for every 1 mole of copper 2 plus discharge at the cathode, 1 mole of copper 2 plus is formed from the oxidation of the anode. So there is no net gain or loss of copper 2 plus in the electrolyte, no change in concentration of Cu2 plus, and hence no change in the color intensity of the electrolyte. And if we have metals with reactivity above platinum, including gold and silver, they are all considered reactive electrode and will dissolve during electrolysis. So this is one of the observations that you will observe. So other than say the anode decrease in size, you can also say the anode dissolve. The problem with aluminium is that although it is a reactive metal in group 13, high up in the reactivity series, because of the oxide layer form, so aluminum electrode is actually inert because of the oxide layer that prevent any reaction from occurring. So in reality, right, the aluminum anode will not be oxidized because of the oxide layer. So the anions will be oxidized instead. So this is just an exercise to reinforce the concept. So in general, this is in reference to water. So if the E0 value is less than 1.23 volt, ion will be oxidized to gas molecules. But if you have a more positive E0, the H2O will be oxidized to form O2. So this is just cheat sheet. For the cathode, if you have E0 more than minus 0.83, the ion will be reduced at the cathode, which means the metal ion will be reduced to form the metal. However, if your E0 value is more positive or less negative, so less positive or more negative than minus 0.83, then the H2 will be oxidized to form water. Actually it should be H2O reduced, right? So if you have this one, yep, H2O reduced to form H2. Okay, looking at this exercise, right, let's look at the first one. If we add potassium iodide with a small amount of phenolphthalein, graphite as the electrodes, okay, let's identify the species present. We have K plus, I minus, because it's aqueous, so water. Don't put H plus and OH minus anymore. The cathode reaction will be this. So copy down from the data booklet, the relevant data. And anode reactions. The overall reaction just combine the equation. So what is really happening is this one and this one. Because this is less positive, so the less positive E0 will be the one undergoing oxidation. So we will expect to see colorless gas form because hydrogen is formed that extinguish the lighted spleen. Phenolphthalein will turn pink because OH minus, alkaline. Yeah. And at the anode, we will have iodine forming, and iodine dissolved in water to form a yellow or brown solution. As for the electrolyte, it will start off as colorless, okay? And it will turn pink at the cathode because of the formation of OH minus. All right? And for the anode, it will turn brown solution. And based on the E0 value, I minus is preferentially oxidized over H2O actually. Yeah. If we have copper 2 sulfate, okay, this will be the relevant information. So copper 2 plus, water, don't you say copper 2 plus will be reduced because this is more positive. As for the anode, the less positive one will undergo oxidation, which is water. And then you combine this one and this one, you form this, eliminating the electrons. And at the cathode, we have copper forming, so that is a pink metal. As for the anode, oxygen is formed, which appears as a colorless and odorless gas that relights a glowing spleen. And there's a reduction in the concentration of copper 2 plus, so the blue color will fade, become lighter blue. When we have H2SO4 as the electrolyte, graphite is still the electrode. We have H plus, SO4 2 minus, and H2O aqueous. So between water and H plus, the more positive E0 value will reduce, which is H plus V. As for the anode, that's why it's important that the water, if you want H2 to be formed, right? Yeah. If you want H2 gas to be formed, it will be better that you acidify the distilled water so that you will have definitely H2 form. As for the anode, you put SO4 2 minus, you will form S2OA. So you choose the one that shows the oxidation. So this is less positive. No, this is less positive. The less positive one will be undergoing oxidation. Minus 1.23. So this is less positive. Okay. So H2O is oxidized. And then the overall equation, just combine these two, the decomposition of water. Okay, these are the observations. And then lastly, sodium hydroxide aqueous, sodium plus, OH minus, and water. So between these, the more positive one will be this one. And the less positive one would be this one. So the OH minus, the other way around, because it's undergoing oxidation. So you choose the one based on their redox potential. And then when you combine the equation, you need to flip. All right. And so on. Okay. Now let's go on to the last few parts of the lecture, the industrial applications of electrolysis. So one important application is the anodizing of aluminium. So we have the aluminium ions. So these are the standard electrode potential of aluminium ions and oxygen. All right. So based on the very negative E0 value, aluminium should be considered highly reactive. All right. Yeah, it is considered a reactive metal by itself. That is not wrong. So by right, it should be having a high tendency to be oxidized than water. Yeah, the one that has a less positive E0 will be oxidized, right? Which should be aluminium, right? However, we don't see that. Why? Because of the oxide layer, as mentioned. So this oxide layer will prevent the metal underlying it to react with, to undergo any reaction. Okay, although this protective layer forms naturally from air, this layer is actually not thick enough. And if you want to further enhance it, you use anodizing to make the layer thicker. Okay, so it will be even more corrosion resistant. Okay, so the aluminium object to be anodized is the anode, and the cathode is the graphite with sulfuric acid as the electrolyte. Or you can also use chromic acid as well. So the reaction at the anode will be the water getting oxidized. So the oxygen form will react with the aluminium, and the surface oxide layer of aluminum oxide will be thickened. So it will not be like a complete, there will be still some aluminium present that allows it to react with oxygen. So the advantages of anodizing it would be, we can use it based on the corrosion resistance and lightness functions used in cookware, electric cables, aircraft, or automobile. The anode film will be hard, resistant to water, and provide good electrical insulator. You can even dye to give some color to make it more aesthetic appealing. Another application is something you learned before at O level, the electrolytic purification of copper. So copper itself is about 99% pure when you first obtain from its ores. Okay, because it's not a very reactive metal, so it doesn't form the oxide so easily. Even if it forms oxide, you can use reducing agent to remove the oxygen easily. There are still some impurities that are mixed with copper. This 1% will be the silver, platinum, iron, gold, and zinc. So if we want to purify the copper further, we can actually carry out this process. Why do they still want to do that? Because yes, it's 99% pure, but this 1% impurity will still affect the electrical conductivity. So if you want to improve the conductivity further, you will need to purify it. Okay, that is the reason. Okay, so we have the electrolyte as the copper 2 sulfate solution. The cathode will be the pure copper, and the anode will be the impure copper to be refined. So we're going to transfer the copper that are pure from the anode somehow to the other side, to the cathode. So the cell potential is adjusted such that the copper at the anode dissolves. So over a period of time, the anode dissolves and a reddish brown copper deposit on the cathode. Now, we have impurities that have more positive E0 value like silver. Okay, so in this case, seems the E0 value is less positive. Okay, so copper will be preferentially oxidized at the anode. Okay? Because we are talking about anode, right? So look at the less positive. So in copper win. So copper will be oxidized, not silver. So silver impurities, right? They can be quite heavy. So they won't be oxidized and they fall to the bottom as sludge. For those impurities that are more reactive than copper, meaning their E0 value is less positive, all right? Like zinc. So zinc will be preferentially oxidized, but then they will just go into the solution and remain there. Because at the cathode, copper 2 plus to copper is more positive. So copper 2 plus is preferentially reduced. So at the cathode, we look at the more positive one. So copper 2 plus more positive, right? So it will be reduced and deposited at the cathode. And zinc 2 plus will just remain in the electrolyte and throw away later or do something about it. The third application is electroplating. Okay, so for this, only metals less reactive than zinc can be used as plating metal. Okay, because if you have a more reactive metal, when they form the ion, it will just remain the electrolyte and not able to get discharged to form the electroplating layer. Objects can be electroplated with chromium, copper, silver, and gold, but it cannot be electroplated with aluminium. Okay. Now, the next part is on Faraday's law of electrolysis. So Faraday's law of electrolysis provides the quantitative relationship between electricity and chemical change. So according to the first law of Faraday's, the mass of the substance or the volume of gas liberated is directly proportional to the amount of charge that passes through the cell. Okay, so from this equation, when a current of 1 ampere passed for 1 second, 1 coulomb of charge was passed. Okay, the amount of substance formed is not dependent on temperature or concentration. Remember that. Okay, so when we have a greater quantity of electricity, then we will expect more electrons, and more electrons means more copper deposited. So in order to increase the mass of copper deposited, we can use stronger current, which increases the amount of electron, or passing the current through a longer duration, which will also increase the amount of charge and hence the amount of electrons. All right. So increasing the concentration will not result in a greater mass of copper. So if you really want to have more copper, the only way is to use higher current or using a longer duration, because these two quantity will increase the amount of charge, which is related to the mass of the deposited metal. So for Faraday's constant, right, 1 Faraday means the charge carried by 1 mole of electron. So that is the definition. So this is given in the data booklet, no need to memorize. So 1 Faraday, so how do they derive it is based on the Avogadro constant and the charge on 1 electron. So they just multiply them and you get 9650 coulomb per mole. So how much charge is carried by 1 mole? So from there, so if I give you the charge of the question, I'll give you the current, you can actually use the amount of charge divide by the divide by the Faraday's constant to obtain the number of moles of electron, and then find out the mole of the metal deposited and hence the mass. So if you can shift the equation, the number of moles of electron can be simply equate as Q over 96500. It makes sense. All right. That will help you determine the number of moles of electrons. Using Faraday's constant. So the lastly is Faraday's second law. The amount of charge to discharge 1 mole of element depends on the charge on the ion. Okay, so in other words, the number of Faradays required to discharge 1 mole of ion at the electrode equal to the number of charges on the ion. So if we want to discharge 1 mole of Na+, it requires 1 Faraday. So you take 9650 coulomb to produce 23 grams of sodium. 1 mole. So 1 mole of magnesium, you will produce 24.3 grams of magnesium. 1930. Why? Because magnesium is 2 plus, ma. So you need to times 2. If aluminum 3 plus, need to times 3 lor. For 1 mole of aluminum, because if you look at the half equation, is 1:3, ma. Yeah. So you need more amount of electrons, right, for 1 mole of that metal to be deposited. Okay, let's look at the question. What is the mass of copper deposited on the cathode if the current of 2 ampere is run through for 20 minutes? So you can calculate by taking the quantity of the charge, and then after that, right, you multiply by Faraday's law. Okay, Faraday's constant, I mean. And then you take the charge, divide by this to get the mole of the copper. And that's it. Another example, last page already. What is the time to deposit 1 gram of chromium when you pass a current of 0.12 ampere? Amount of chromium deposited, you work backward lah. You'll find the mole of this, and then use the half equation to find the mole of, should I say, charge needed. And then once you get the charge, you multiply by the amount. You find the amount times the charge. You get the quantity of charge. And then you divide by the current, you get the time. How about this one? Volume of oxygen at STP when 2 ampere is passed through for 30 minutes. So you calculate the quantity of charge. Okay, and then you can use this method, which is shorter, or if you prefer a clearer method but longer, we should want to consider one time. Very confusing, right? Not intuitive, right? So after you calculate the charge here, right? All right, you can actually divide, because this you can find out the amount of electron here. Okay, but look at the half equation. All right, then the mole of oxygen is 1:4. So amount, that will be electron, ma. So amount of oxygen is just mole ratio. This is another way of doing it. Likewise, for the volume, you can just use the STP, not RTP. So it's 22.7 to get the volume of oxygen. Last question for this topic. A current is passed through 2 cells connected in series. The first cell contains XXO4, while the second cell Y2SO4. The relative atomic mass of X and Y is in the ratio 1:3. What is the ratio of the mass of X liberated to that of Y? So you can let mx be the mass of, you use algebra to solve. So mass of X liberated and mx is the molar mass. Okay, because their ratio is in terms of atomic mass. So I will use this. Then same for this one. So for the same, because they are in series, so they are having the same quantity of electricity. Okay, so the amount of electrons is the same. But one is X plus, X2 plus, the other is Y plus. So clearer if you write down the half equations, you see the ratio. So if you look at this, the X and Y is the ratio of 1:2. So how much X is half of how much Y? Okay, so to find the mass ratio means first of all we take This is for X. So X, the mole of X is half of the mole of Y. Okay? So after you just shift this thing downward. So it's just shifting Y to here and MX to there. Okay, they said that MX, the molar mass, MY is 3 times. So you just sub in this. So MX over MY become 1 over 3. So that's how you get this. So it's half the half 3, 1 over 6. Okay, so you can actually just use the number of moles, put in the algebra expression, and find the ratio. Okay. Okay, so I hope you enjoyed today's lesson. Thank you.